Today we'll be starting our measurement unit. And so the first thing we need to talk about when it comes to measurements is making sure that we know the precision of our instruments, what it means to be precise and accurate, and then talk about significant figures. So we'll first start with some definitions here. So a measurement is a quantity that has both a number and a unit. So 35 isn't really a measurement, but 35 grams, now that would be a measurement because it has both a number and a unit that we're talking about. So it's important to be able to make our measurements and make sure that we are recording them correctly. Now, to be accurate, well, accuracy means how close your measurement comes to what we call the actual or true value. So these are things that have been tested and have reliable sources. And so in order to be able to evaluate our accuracy, we have to make a comparison of our measurement to the true value. As for precision, this is a measure of how close a series of measurements are to each other. And so the way we do that is you have to have at least two or more values of the same type in order to see if you're precise or not. So I love this graphic with bullseyes. Imagine you're throwing darts at a dartboard. The first depicts that it's accurate and precise. So remember, accurate is how close to our true value. So let's treat the bullseye as our true value. All four are within it, that's accurate. And precision is how close they come to each other. We are very precise because all four are very close to each other. As for the next one here, we're not accurate because our darts did not even come close to our true value, but we are precise because they are clustered very close. So our precision is good, our accuracy is not. The next one, I'm going to start with precision. We're not precise because of how spread out our values are, but if you were to take the average of all four of these, you would end up around the bullseye, making us accurate. And lastly, not accurate, not precise would be none of them are very close to each other and we're not even close to the true value. And so in lab, we have a way to actually measure our error. And so the way we do this is we first have to have an accepted value, which is the correct value based on reliable sources. And then our experimental value is what we measure in lab. So you guys will be doing this on lab reports in the future. And so that error is going to be the difference between the accepted and experimental value. And so we have a nice formula here. And so how it goes is we take our accepted value, so what we looked up or what I gave you, you're going to subtract your experimental value, take the absolute error of it, so that should always be positive, divide it by the accepted, and then multiply it by 100 in order to get into our percent. So we're going to do an example here. So let's say in lab you measured the density of aluminum to be 0.25 grams per milliliter. And I tell you the accepted value is 0.7 or 0.27. So what's our percent error? Well, let's plug it into the formula. So we would take the absolute value of our accepted, 0.27 grams per milliliter, and subtract our experimental, so what we got in lab, 0.25 grams per milliliter, and take the absolute value of that. Then we'll divide it by the accepted again, so 0.27 grams per milliliter, and making sure to multiply that by 100. If you plug this all in your calculator, you would get that our percent error is 7.4%. So now that we have a relative idea on accuracy, precision, let's talk about a little bit more about how we get these values. How do we measure things in lab, from graduated cylinders to mass and volume. So let's move on to the next section here, significant figures. So this will be a little bit difficult as we get used to it, but the more we practice, the better we get. So the biggest thing to understand is we are making estimations based on the precision of our instruments. So if I were to look at this instrument to the left, I see that each of these goes up by 1. So this line would be 31, the next would be 32, 33, 34, and we're back up to that 35 mark. So I'm going to estimate that the bottom of my meniscus is between 34 and 33. So let's record that as 33.5 milliliters. So if I were to count, this has 1, 2, 3 significant figures. Because we are certain that the measurement is at least 33 milliliters, but we know it's less than 34. So that estimation goes between those two values. So you always estimate one place further than what your instrument gives you. So if it gives it to you in 1 milliliter increments, you are going to estimate to the 10th. Let's practice this again to this figure. If I zoom in on it, I already have the numbers recorded here. This line almost seems like it hits exactly at 43 milliliters. But because of this needing to estimate one place further, I'm going to record it as 43.0 milliliters. We can tell that it's exactly at 43. So we have to include that 0.0 to convey that our measurement, our instrument, goes by 1 milliliter increments. So because this division, the smallest division on here is 1 milliliter, we will estimate to the nearest tenth even if it's exactly on one of those lines. And we still have 3 significant figures. This 0 is significant because it tells us how exact we're being. So let's go through one more example and we'll talk about the rules. So if we look at this object, again, I'm going to zoom in a little bit for you guys. We can tell that it is between 0.035 and 0.036. So, recapping this in words, we're certain that it's at least 0.035 centimeters, but it can't be more than 0.036 centimeters. We're then going to estimate one place further and estimate to be 0.0355 centimeters. So we are going to count our significant figures again. The last 3 digits are the only ones that are significant. So we still have 3 significant figures. So the key thing to note here is zeros at the beginning of a number are not significant. They are just placeholders. And we'll talk about that more when we get into scientific notation. So let's run through these rules on significant figures. This will help us determine the quantity of how many we have. So, all non-zero numbers are significant. This is the easiest rule. So if anything is not a 0, it's significant. So the first example of 2.15 centimeters therefore has 3 significant figures. The bottom one has 5 numbers that aren't 0, so it has 5. So where things get tricky has to do with the zeros. So I'll go through each specific scenario. The first of which are leading zeros. So the key here is that they will come before or after the decimal, but they have no non-zeros to their left. I apologize for my weird formatting here. They are never significant if they don't have a number that's not 0 to its left. So looking here, you would look at this group of zeros. There's no non-zero number in front of them, so they are not significant. That means we only have 2 significant figures, the 2 and the 3. Looking at this next example, very similar. There's no number in front of that 0 that's not 0. So only the 1 and 2 are significant. So we have 2 significant figures again. Number 3 is a little bit easier here. And so we have what are called sandwich zeros. So if we have zeros that are sandwiched between numbers that are not 0, they have to be significant. So we have a total of 5 significant figures for this one. The one below, if we count every number there, because we have our 2 non-zeros sandwiching our 0, that is 3 significant figures. Now trailing zeros, these get tricky in the sense of decimals. So the key here is if you have zeros at the end of the number, look for the presence of a decimal. So if there is a decimal, they are significant. If there's no decimal, they're not significant. So what we would say is we first ask, are there numbers that are not 0 to the left? Yes. And then we ask, is there a decimal? No. So these cannot be significant zeros, therefore we only have 2 significant figures, the 7 and the 8. Now, taking a similar looking number, we first ask, of these zeros, are there numbers that are not 0 to the left? Yes. Is there a decimal? Yes. So they are all significant. That would give us 5 significant figures. Now this bottom one is very similar. We have numbers to the left that are not zeros, and we have a decimal. So you still count all 4. These would be 4 significant figures. Let me give you one more example. Let's say we have this 7,800.00000. These would all be significant. The reason being is as we keep adding these zeros after the decimal, we are saying we are more and more sure how exact we are to this value. And last thing here is just be aware of exact numbers. So we say they have infinite significant figures, but the true thing is we just have certain numbers that we can't, they don't change our significant figures when we do calculation. So we'll get more into this when we talk about conversion factors later.